Maybe we should start now.
Yeah.
Okay, ladies and gentlemen, we start this lecture series from CMSA of Harvard University in joint collaboration with the YMSC in Tsinghua University. We have a sequence of talks in memory of 4 distinguished mathematicians, Atiyah, Bott, Singer, and Hirschberg. And Singer died just a few weeks ago. So all of them are now history, but they like the name. I call them Gang of 4 at one point. They are very happy to be called that name. So we will dedicate these lectures in memory of these 4 great mathematicians. So Maxim will start the first one. And I will turn the lecture to chair by Paul Seidel. See there? Paul Seidel.
Yes.
Paul.
Hello, everyone.
Yeah, good.
So it is a great pleasure to have Maxim Kontsevich here, who is professor at IHÉS. I think it's very hard to be in mathematics and not have heard of Maxim. So he has a Fields Medal from 1998 and a Breakthrough Prize 2014 and many other awards. You know, he started with spectacular early work on Vasiliev invariance of knots and on the cohomology of the Lee-Mumford spaces, and then turned to quantum cohomology and mirror symmetry. And, you know, through homological mirror symmetry has really transformed the field. I like to say that he's given us sort of stereoscopic vision. And he has, you know, developed this, you know, much further, you know, through work on wall crossing formula that was partially motivated to that, and Donaldson-Thomas structures. But he also has contributed to many other areas, such as birational geometry and actually ergodic theory. And I'm sure some things that I forget. And so the mathematical community, I think, is eternally thankful to him for creating entire areas in which people can make their career, and such as me. So today, his title is on the history of quantum cohomology and homological mirror symmetry. Before I turn it over to Maxim, I would like to make a practical suggestion for asking questions. If you have questions, please just ask them in the chat. We have a very large audience. This is the best way. Then when I think it's a good moment, I will interrupt Maxim and I will not call on you. Instead, I will just read out the questions and Maxim can go and check the chat or just listen to me. You should have a chat box there and then we'll have the questions answered. Maxim.
Okay, thank you very much. Yeah, it's a great honor to start this lecture series, and I knew this 4 great gentlemen very well. In fact, it was very influential in my use of all of them. But yeah, so I'll divide my talk in several pieces, and it will be kind of really highly personal and maybe I think biased version of history, but it's how I remember thinking. And so what I'll tell just what I saw and what I thought about at some time. So the first, I'll start kind of with chapter -1, kind of before. There were several things which I happened to knew, and it was really instrumental to get the idea of homological mirror symmetry because I was educated at Moscow State University, and there was some really remarkable thing happened in 1987. Alexei Gorodentsev and Alexei Rudakov wrote a nice paper when he introduced exceptional collections and things like this. Actually, Alexei Gorodentsev was the same year in university as me, so I knew him very well. I know him very well. Yeah, and they based on some early work, they look on some early work by 1985 by Drezé and Leportier. Maybe I'll share a screen for a second, and unfortunately people who are in real audience will not see them, but it'll be really little think, just a second. I'll share screen for a second for you and not for people who are really here. Okay. So you see some picture. So there is try to classify vector bundles on CP2. Bundles on CP2. And they make some kind of calculation of what is going on with respect to slopes and things. And there are rigid bundles, which you don't have cannot deform, and they wrote a picture which is what you see on the like this. The row, the event of the base is picture which you see on the screen, that people in real audience don't see it. And there are some denominators which are ranks of these exceptional bundles, and there are 1, 2, 5, 13, 29, and so on. Now, so there's remarkable ranks of bundles on CP2 which can be rigid. So now I stop sharing. Okay. Yeah, so we get these numbers, and Gradentsev and Rudakov understood what is the meaning of these numbers. These are called Markov numbers. Maybe you consider equations, Markov equation in 3 variables, consider solutions with integer solutions. And numbers which appear as integer solutions are the first solution is 1, 1, 1, then 1, 1, 2, and so on. And then we get this 13, 29. And then found what is the origin of all the story. They found some notion of mutation. Namely, they realized that the game is about triple of line bundles. Or of 1 or 2, and then we start to modify in various ways. For example, consider kernel of 1. Why write 3? Because there are 3 linear independent morphisms on P0, 1, and 3 homogeneous coordinates on P2. We consider kernel of this map. Then second will be 0, then P2. Or we make some co-kernel. Yeah, so you start to kind of permute first 2 elements, or you start to permute 2 second elements, you start to act with some break group. And then we produce all these remarkable vector bundles on higher rank, which are all rigid. And then immediately generalized to projective space, formulated the whole story. And then it leads to some kind of really spectacular development at the end. It was in 89, 90. 2 of my good friends, Alexei Bondol and Misha Kapranov, developed the whole theory about the whole story, kind of open a new world. They introduced something called semi-orthogonal decompositions of triangulated categories based on this work of Gradentsev, Rudakov. Introduce braid group actions on such guys. Then introduce a notion of a sec functor, something which Jean-Pierre himself didn't introduce. It's namely R home. If you consider 2 bundles, consider all X and take dual space. It should be our home from F to S of E as a set functor. And this is just twist by canonical bundle and shift by dimension. And then also they introduce DG categories and saturated categories. It's some kind of abstract notion which encodes coherent shifts on smooth projective variety and some twisted complexes. it's something to do with DG categories and related to related categories. Yeah, so there, a lot of work was done, and Bondal Capran, a little bit older than me, some 2-3 years older, and what we discussed this is the problem method, and I was kind of an eighth of all this development. Yeah, so this was one story. So there was this kind of, I was really lucky to know about all this. But also I have kind of, also have some luck in other direction. For example, Vladimir Retok around 1990 introduced me to Stashev infinity algebras and L-infinity algebras, and work by Jim Stashev. And A-infinity algebra is really important. I think it's a story. It's infinity algebra is maybe two-graded supervector space. Let's see, two components. And then I get a lot of maps, M1, M2, M3, which is odd, even, odd, and so on. With infinite sequence of maps. And then you write these operations like this, and you write some higher associativity condition. You insert one operation in another operations and take all possible summation, takes alternating semi-appropriate things, and then you get 0. And then it implies that algebra is M1 is differential, square equal to 0, M2 is associative on cohomology, and yeah, so it's some kind of generalization of associative algebra. Yeah, so and you see this picture is kind of planar. You draw on a picture, you draw planar trees with two inner vertices. Now then there was something else. Again, for my kind of older friends, Dmitry Fuchs introduced me to work by Thurston. And then there was also work by Robert Penner, which gives a cell decomposition of modulus space. Modulus space of curves with some points, speaking for Rn and maybe at a point infinity. And cells are represented by ribbon graphs. And these are kind of also ribbon graph. Let me draw a little bit thicker. And okay, that's actually I use in my proof of Witten conjecture. This here about year 90. And then this thinking about this, it was really before mirror symmetry. I started to think we have this nice identity for infinity algebras. You get these ribbon graphs in general, where one can marry them together, and this lead me to some so-called idea about graph cohomology. And for example, one of the things which I realized, if you have finite dimensional infinity algebra and you get scalar products, such as these things give scalar invariant, cyclically invariant functionals, then you can produce cohomology classes of modulus space of curves, just treating this as a Boltzmann weights for some kind of lattice model, for instance. Yeah, so this and in the winter 91-92, I went to Harvard for 3 months and I gave a few lectures about graph cohomology. I started to write this paper, but it was really before mirror symmetry. Yeah, so you see that I kind of was really well prepared for the advance of mirror symmetry. And now, in the beginning of 90s, this really things exploded in mathematical physics. Yeah, so this was Wheaton's conjecture. Integrate of modulus space of curves of product of some classes and get solution of WDVV, the things which we solved at that time. But it's not really mirror symmetry. Then Waffa introduced, actually, I don't know who first, Waffa or Wheaton, quantum rings. And that was first kind of informal idea. You have X, this target, your theory, two-dimensional theory, two-dimensional theory. In fact, it will be super conform of n equal to 2 UFT. No. And it will be some scalar manifold. You have to secrets manifold like CPN or proper surface in CPN give the algebraic equation. And then you introduce a multiplication cohomology of X depending on parameter, on some small parameter. When t goes equal to 0, you get usual multiplication. So it's a deformation of usual multiplication. And the informal formula was the following. If you get, let's consider 3 cycles, C alpha, C beta, C gamma cycles, and we identify homology with cohomology. And now I want to consider product of C alpha gamma. And I discuss the product using Poincare pairing with cycles C gamma. And the formula is the following. It's sum over all maps of V1 with 3 points, 0, 1, infinity, to X, homomorphic maps, such that T2 integral of Keller form of this V1 is an integer, degree of the curve multiplied by and maps such that phi of 0 belongs to C alpha, phi 1 belongs to C beta, phi infinity belongs to C gamma, and you count only kind of isolated maps. So you get some polynomial in T. And the basic argument here, kind of invented by physicists, it was based on Carol Wink and so on, White's associative product. The idea, you do the following. You consider curves with 4 points and with given cross ratio, and start to map to my manifold and try to intersect these 4 guys with given cycles. This thing shouldn't depend on the cross ratio. And now consider limits when t goes to, say, infinity. And in this case, the curve decomposed by union of 2 rational curves. Or t can go to 0. Then we get these things. And you get 2 sides of a associativity equation. So you get quantum multiplication. As quantum multiplication is a compose them in one way or another. Yeah, but it's multiplication, it's commutative. You get commutative associative product. Yeah, and then Wheaton wrote some kind of very influential paper, which I read for several years. Yeah, but it was kind of discovery of quantum cohomology. But then also came mirror symmetry. And for mirror symmetry, it's kind of different story. At that time, physicists, when they say Calabi-Yau, they mean varieties, mean three-dimensional Calabi-Yau varieties. And we can see this three-dimensional Calabi-Yau varieties is two homological class. And then Hodge numbers, they form Hodge diamond of essentially depends on two numbers, A and B. Will be, because H03 will be 1, H10 will be 1, but then we get H11 and H22, H12. Maybe H11 is called A, B, these two parameters. And let me share you a screen. There was a remarkable discovery. So people make calculation with about 10,000 Calabi-Yau threefold, which they can produce complete intersections of weighted projective space, things like this, and they make a statistics of this. So wrote A and B, and just a second. Let's just go to a second. Find the file. Well, by the way, I want some kind of feedback. Do you hear me?
I can hear you fine.
Yeah, we can hear. Yes.
Okay. Okay. Good. Yeah.
Yeah.
Yeah. So this paper, which picture, which I don't want to show people know. I get kind of statistics of whatever A minus B, A plus B, and I get some very symmetric picture. Yeah, it's very impressive. I remember I attended one of conferences, was completely struck by this very symmetric picture. So it means that for each Calabi-Yau, family Calabi-Yau, parameters A and B, there's another families with B, A, and R permuted. That's the name of mirror symmetry. You make reflection of Hodge diamond. And then, yeah, that's, and then there was this prediction by Candelas, De La Osa, Green in Parks. And there was a book by collection which was published by, collected by Yau and published in '92. So again, maybe I share a little bit screen. What is this? It is this book. It says on mirror symmetry and mirror manifold, and which contains a lot of things. Yeah, just one can try to read the content of this. Not all content, it's already half of the content. It's already, it's very impressive. Yeah, so if you read the content, you see the paper by Candelas, De La Osa, and Kumrumbach about quantum rings at Witten, about mirror manifolds, and David Morrison, who explained first mathematically what is going on, Picard-Fuchs equation, variation of Hodge structures. And okay, so maybe I'll stop sharing because it's okay. Yeah, so this was this prediction by physicists which gives how many rational curves of each degree on Calabi-Yau threefolds, and get numbers, and it's related to variation of Hodge structure, very crazy way explained by Morrison. Yeah, and then Butterick and Boris and Van Straten introduced very general family of Calabi-Yaus to play with, and complete intersection toric varieties, which was became a major playground. So it was really kind of explosion of information how homological mirror symmetry was born. In the winter 92-93, I was visiting, no, not Harvard, but Princeton Institute for Advanced Study. And I think it was maybe in December, I heard a lecture of Kenji Fukaya, So it's kind of end of 92. Foucault gave a lecture where he, in some special case related to Casson invariance and gauge theory in 3 and 4 dimensions, a special class of symplectic manifold just introduces this fantastic idea of have a category associated to symplectic manifold. So we have symplectic manifold, y with some symplectic form omega. What he proposed to take Lagrangian manifolds as objects. And now we define forms between them. Actually, we define it in 2 different ways. If L1 is equal to 2 and 2, we say it's cohomology of this L1 and 2. And if they're different and intercept transversally, then consider vector space generated by intersection points. And how we introduce, then I introduce some differential in this guy. It will be infinity category. And exactly cyclically ordered, as I thought before, by completely abstract reasons. Namely, you define differential, counting holomorphic disks with boundary and union Lagrangian manifolds, and in 2 points. It will be M1. And in general, consider this holomorphic polygons. And get the infinity category, kind of cyclic infinity category. It's generalization of infinity algebra. Yeah, and then something really clicked in my head. I realized the reason I got the idea that its mirror symmetry should be equivalent of this Foucault category of one manifold and the derived category of coherent of another manifold. And what was the reason? Kind of the reason was very simple. So what he's tell about these predictions and so on, that if you consider 2 dual manifolds, X and dual Y, let's say X will be complex structure, then the following things are equivalent. 2 rings are equivalent. We consider direct sum of homology of X with coefficients in exterior power of tangent bundle. And what here goes on, consider quantum multiplication on cohomology of Y. Yeah, so that was the claim. And how one can understand quantum multiplication? It means that you map sphere with 3 points to Y. Yeah. And what is my idea was the following: this you map sphere with 3 points to Y, and I claim it's the same as a map of disk with 3 boundary points to Y squared, such that the boundary of this goes to diagonal. If you have a map and boundary goes diagonal, just have first projection, second projection that coincide with diagonal, and put together, you get a map of CP2. So you relate disks and spheres. And what does it mean? And this guy will be X group or home group in Foucault category of Y squared from diagonal to itself. And these things is a home group in coherent shifts on X squared from diagonal to itself. Yeah, so you see that you get category, you get identity functor. And what I see that if you have any whatever GG category, then consider kind of category of functors and consider home from identity to identity, functor from C to C. This is something called Hodge cohomology. It can be defined for so algebra, categories, whatever, and it's responsible for deformation theory. Like you consider H1 of X is tangent bundle with deformation of complex structure, or H0 of H2 will be quantization, the non-commutative deformation of X. Yeah, so kind of you knew it from talking with Alexei Bondol about this Hodge homology, 1 and 3. And so we see that kind of we get Hodge homology of two categories coincide, and then the guess it was the category coincide. And I was so that's what was going on. And because I was in Princeton, I just ran to Witten and Deligne and said, oh, I understood what is mirror symmetry, explained them this whole story, and then start to kind of got very excited and start to talk. It was so the idea came something like maybe in January '93, kind of maybe months after Foucault talk. Then I started to ask, to understand what is going on. What is the product on Hodge homology? I remember ask this. I think I talked to Jim Stashev and Murray Gestenhaber, who invented this cup product. He was in Philadelphia, very close to Princeton. So I talked to him. I said that I understand this bracket on homological Hodge complex. This is false deformation. But why is this cup product? Where does it come from? And for them, it was for him, this bracket was most difficult part, but cup product was most obvious. And I kind of started to be surprised in the opposite way. And then I asked Deligne why cup product is commutative. And Deligne explain me the following: that when you consider X group from identity function to itself, here we get two multiplications. One is just compose X groups, and another get tensor composition of functors, and identity composes identity is identity. So you get kind of in the same space two products, and each product is morphism of algebra with respect to second product. And then you do the following: you consider some product in some order, alpha, beta. Then you write alpha, beta, you add 1. Then you stay alpha, beta, 1, 1, and you decompose. Then you start to make it alpha, beta, 1. You exchange. And then you make like this. Yeah, so do such little diagram and kind of to change on your whiteboard this to I think it explains commutativity. Okay, so it was very good, and then I left Princeton, and then maybe in March, and then in May. Deligne wrote a letter to many people, to again all responsible people, but not me. Somehow, yeah, definitely I treated his questions. So it was Deligne's letter, and he proposed a conjecture, kind of coming from this picture, that on homological Hodge complex of any algebra, acts DG operate of chains in little disk operator. So what is going on? You can see the configuration of, let's say, like 4 disks inside the disk on a plane that form some space. You can compose the spaces putting one thing to another. So the form operator, it's like multilinear operations, but spaces are non-linear objects, and you're replaced by something linear, singular chains of the space, and then composition goes to position of operations. It's, yeah. So it was a conjecture, and then yeah. So it was a conjecture. He sent a letter to many people, and then in '94, I don't really want to go to controversies. There were 2 solutions proposed by Gessler, Jones, and Voronov and Gerstenhaber. But then a few years later, it was discovered that, if I'm not mistaken, there was some kind of really deep error in those arguments. And the things start to think again. And what it's, I'll later return to the story. Yeah, so at some point with Jan Sobelman, we return to another proof. Now, so it was a little bit of controversy. Yeah, okay, so so it was kind of offshoot of mirror symmetry. There was this nice question in abstract algebra, which turns out to be quite central to the whole story. Then I returned back to Max Planck Institute in '93, in June. It was Arbeitstagung talk, Arbeitstagung meeting. It's annual meeting organized by Fritz Hirzebruch, as you know. And here on this meeting, it was really concentrated about mirror symmetry. So the first talk by Yuri Manin, then second talk was by me. When I proposed this idea about infinity algebras of mirror symmetry, and then Bin Ruan was talking about symplectic version. Yeah, so I gave this. So it was really first public exposition on this two Witten. And I remember this effect of those late great differential geometry, James Sills. He told me, okay, you nailed it. So next year we'll understand everything. It took more than next year. It took maybe several decades, I have to say this, to finally finish the project. And then in '94, I gave a plenary talk at ICM in Zurich. Explaining and giving more meat and as examples of this mirror symmetry conjecture. Yeah, it was a bit reckless. I didn't have any good evidence. We have maybe one little example of elliptic curves, but presented very, very detailed conjecture and so on. And then after I gave a talk and then it was kind of published, then I just realized that there was really something goes wrong. Something deeply goes wrong. You can have Lagrangian manifold and you have holomorphic disk, this boundary on this Lagrangian manifold. And then it gives something M0. And M0, it's something which we do not allow in infinity algebra. We start with M1. So M0 was element in algebra. It means that it's not an object. Yeah, and I kind of was a bit in a panic mode. So if you read, maybe I'll just share. Just a second. Things. Yeah. So I shared in the published version of my talk, not an archive version. I have no note added in proof. I realized there's a serious flaw in Foucault preprint. There is this stratum in the whole story which you forgot, and all things kind of falls down. So maybe there is nothing in the whole story. Yeah, but still, the story is so nice, and there's one little example which works. So yeah, so it was kind of really a bit unpleasant moment. Yeah, and what was going on? So for a while, for several years, there were kind of two things. This Foucault categories was under many question marks, and here what you do with kind of polygons, yeah. And there's a quantum product. The quantum product, from my perspective, it's secondary things which appears in Cauchy cohomology. It's on sphere. You get sphere and 3 points. Yeah, so instead of disk, you get a sphere. And this is theoretically it's much simpler. And this nobody really worked on it for several years. It was kind of forgotten things, except maybe Foucault we discussed. but quantum cohomology, what was really developed at this time. So what was going on? Yeah, so it was kind of temporarily forgotten, again, in same 94, before this Congress, there was really a lot of development. So first of all, I came to the idea how to define this quantum multiplication, Gromov-Peterson invariance. There's also a notion called stable maps. It's analog of the Lee-Mumford computation for abstract curves. When I get the curves decomposed by some out points, and to decompose in several pieces. And the condition that usual notion of stable curve, it's each component, if you remove all double points and mark points, you get negative value per piece, or you get curvature -1. And here it's a different story. So you get a map from a semi-stable curve, which is a semi-stable curve with mark points. So your target manifold, right? And the condition that stability is only on components which contracts to a point. Each component which contracts to a point should have negative Euler characteristic. Yeah, so it was a little modification of the Lee-Mumford space, but it was right notion. In fact, up to now, I don't know any physical derivation of this. It was kind of good idea, but it's pure mathematical idea. And also people in symplectic topology, Parker and Wolfson, at the same time had this idea. Yeah, but it was a kind of definition, use stable maps. And then the idea is that this guy should have virtual fundamental class. Why so? Because if you consider a kind of a derived tangent space, this guy you get a complex of lengths 2, because curves have only 0 in first cohomology. And so it means that its dimension of this guy is bounded below by Euler characteristic of this complex. One can formulate in many ways. It's like intersection of two submanifolds and submanifold, but intersection not transversal. So that dimensions can be only larger than expected dimension. So it should be expected dimension. Yeah, so there's no theory about it, but it was and then there's also kind of very nice calculation which I made for this associativity equation, WDVV equation, just in case of CP2. It was something which physics is never done, but done, and then one can calculate a number of rational curves of degree d passing through 3d minus 1 points. You get some numbers 1, 1, 12, line satisfying. Eventually, it's related to Penn-Levy 6 equation. Yeah, so it was some nice example. And then with money, we wrote a paper about axiomatics of Gromov-Peterson invariance. Not really constructed them, but in some open convex cases, it really works. Axiomatics of Gromov-Peterson invariance. So what things should satisfy? And then also in 94, deleted it after the slide. I think I tried to calculate. I realized that there's some, with this at least heuristic, I can try to calculate how many this rational curves on quintic C-fold through the following idea. We get quintic C-fold. It sits in CP4. And so it's given by some equation that you get some section of 4, 5. Given by equation of the before, given by S equal to 0. The section vanishes. So margins for the 5 and 5 variables. Now the idea was the following. You consider stable maps of P1 to CP4, not to quintic C4. And this is one of nice examples of this virtual fundamental class. This guy is smooth orbital, smooth compact orbital. And if you get a map from a curve to, in general, it's not CP1, it could be tree of P1. Then construct a bundle. You consider pullback of 5 and take its sections. This is some vector bundle, and this S induce a section of this vector bundle and map to zeros, exactly zeros of this section. So it means that what I have to calculate, kind of like earlier expected number of zeros. It means it's top chain class of this bundle. I get a huge bundle of some huge space, and how to calculate this integral. And then, thanks to Raoul bot, we have a tool how to do it. Maybe we start to use some action of some group, like just choose some coordinates here and take a rescaling of coordinates. I get a huge torus. And now consider fixed points. Fixed points one can analyze, and then one can make a sum. And I wrote a pre-program, but when I made the first calculation, I really spent the whole night at Max Planck Institute trying to guess, to understand what I have to calculate. And I said to my wife, sorry, I really have something important to calculate this night. And then I calculated with Paris and so on. It was pretty heavy, and then I get right numbers, exactly what physicists predicted. Yeah, so it was, and then I wrote some paper about enumeration of rational curves with this torus section, and proposed some heuristic about virtual fundamental class. Yeah, so it was this development in 94. Yeah, but it was really very, very heavy formula. And eventually, one can write as the critical points of some functions infinitely many variables, so it's really hard to do it to computer. Yeah, but at the time, I think pull it up to degree 4, but it was a long calculation. Then after that, I went to got a position, solid position in Berkeley, and I went to 95. I went to 1994, late 94, 95. I was in UC Berkeley. I was professor at Berkeley for 9 months before I received offer for IHÉS. Yeah, it was my only teaching career. Now, so there was something interesting that was going on here. Yeah, Alexander Divental was my colleague here, and he also was interested in mirror symmetry. He has his own viewpoint, very different one, and then he decided to kind of go through my calculation, see what one go on. We started to discuss it. Then I was a little bit distracted, and then he said, "Okay, so I finished the paper. Maybe we'll have a paper, so everything's fine. Everything fits together. I can have a proof. Good." And then I look on this proof. Now I understand kind of 90% of the paper. It was, but the rest, the real kind of essence of the proof, I was kind of puzzled. I wasn't able to understand the case. So sorry, I cannot do it. What do you mean? I really don't understand. And I remember it maybe maybe about a year, I visited Harvard and talked to Calabi-Yau. He said that he spent the whole year trying to understand this last 10% of the paper. Didn't succeed as well. So it was, yeah, so it's kind of strangely written part of the proof, which we weren't able to understand. Eventually, Yau found his own way. But some people understood. I remember I talked to Decomposition. He said that it's okay, yes. So it's everything. I think eventually there's no controversy. There was some kind of bad feelings at that time. But but there was something really something surprising for me, which I extracted from given type paper. To calculate not only on this Calabi-Yau hypersurface, but on Fano hypersurface. When degree of equation is small, the number of variables. And what he get for Fano, he said that the mirror dome is a variety together with a function called potential. Which is kind of new idea. And in fact, he wrote that he has this idea already in 93, but I didn't notice it. I don't know where he get it. And this idea turns out to be extremely important. Yeah. So in fact, in Berkeley, in this again, when I was in 94, I also gave a course on deformation theory. Because I see that all this Hodge cohomology deformation of categories, start to think about deformation of everything, and that gives some kind of nice this course. And in this course, before I learned about this potential, just some kind of completely formal reasons, I realized that if you have algebra and central element, it gives you again kind of deformations of your I think this M0 story. In particular, if you have variety function, you get new category, and which people later call matrix factorization. Namely, consider two bundles on X, and with and some kind of two differentials, T1, T2. So the product of this maps, it will be W times the identity map. So if you realize your bundle, you get some kind of matrix valued function, like rectangular, square matrix valued functions. You get two functions, and applying one or another, you get scalar function, which is a good potential. Now this form again is this category, and it was my course, but it wasn't. It was before 6. It was for completely formal reasons. I introduced it, and later, really many years later, Kapustin and Orlov picked it up and called singularity category. Also in my course, I kind of think was because I was interested in mirror symmetry. I was surprised by the following fact. If you consider this Foucault categories, they naturally have deformation given by cohomology of your variety. So the modulus space is smooth. And what goes for complex varieties? It was a very nice Jan Todorov theorem. And Andrei Todorov was actually a good friend of mine. He lived not far from Berkeley in Santa Cruz. So we talked a lot with him. That modulus space of Calabi-Yau varieties is smooth. And in my course, I kind of propose a generalization of Jan Todorov theorem, namely consider the algebra, consider X will be Calabi-Yau variety, which will fall away, consider section of polyvector fields and D bar forms. Get some DG algebra. Then it's formal. So this modulus space is smooth. Derived modulus space is smooth. It's generalization. Now it was really to understand why these two categories are the same, why the modulus space is the same, when particularly why it's smooth. Yeah, so it was generalization, generalized Jan Todorov theorem, and then the physicists already talked about this for many years. It was Nick Warner, I think, in really early 90s, started to speak about potentials and isolated singularities given quasi-homogeneous singularities given conformal field series. And yeah, so it was something which eventually we saw it. And then a little bit later, I came to this idea of another category. It's kind of B-model category, holomorphic category. And then essentially at the same time, I got the idea as the following. If you get this potential, say with isolated critical points, then I can do the following. You consider, first you consider some disk containing the critical values of potential, and now take this disk in union with, let's say, negative axis, and consider Lagrangian manifolds in your variety Y, such that projection of Y lies in this union of ray and a disk. And so there's some high dimensional systems project to something essentially one dimensional. Here will be two dimensional, here will be one dimensional. And how we define homes in this case? You define homes, you see that they get a little trouble because they really intersect not transversally. Because they project to the same line, you see that immediately intersects with full ray. And you tilt a little bit N2 and make transversal intersection. tilted too, so the projection will go to a little bit different rate. Yeah, so it was this idea, and I started to have a student, Sergei Baranikov, at Berkeley at that time, and we was very excited about this. Yeah, so this now is called, Paul Seidel really took it seriously, but maybe about 2000, and it's okay, Seidel category now. Yeah, so so there's a kind of new world of varieties with potential when one can have the whole story. Yeah, so there's something which we've done with Sergei that then what to do with potential. So what we discovered several things. First of all, in this picture, one can consider subcategories associated to individual eigenvalues, and you unseparated make this pass, you get exactly similar orthogonal decompositions of Gondel and Kapranov. So you get collection of subcategories, so there's no Holmes in decreasing order. And the whole story is generated by them. And when I take like CPM, then the potential is something like Z plus 1 plus Zn plus 1 over n. C star n to Z is potential. And when I consider critical points, you get root n plus 1 roots of 1. And if you connect with this point, you get a classical like Belinson semi-orthogonal decompositions of projective space. And then those kind of pictures that in general should get semi-orthogonal decomposition for this of derived category of definitions and Fano varieties from this critical values of potential. This late Boris Dubrovin also came to the same ideas independently later, and yeah, I think it's actually there's a huge future in all story associated to birational geometry, and expect a lot of application, but it's not this is the time to talk. So it was one story. Then there was a next story, which was Sergei came with me also to France and became my postdoc here. So we proved several things. It was something which you now wrote. It was the generation of Hodge to the RAM for this variety with potential. Namely, if you get a map from variety to C, and suppose it's a proper map and Y is smooth. Let's say smooth projective variety, complex variety. Then what we prove that rank of the following two things. It's consider hyperhomology of Y, consider shape of forms with multiplication by BW is the same as rank of the same thing. Consider forms with a risky topology is G plus BW. It's actually a really interesting result. In order to prove it, it's analog of the generation of Hodge classical Hodge theory, and the classical Hodge theory is some Laplace operator, Sobolev spaces, and we have to redo all things. Laplace operator, Sobolev spaces, some kind of analysis. It was a bit heavy. It was actually first example of irregular Hodge theory, and later Mochizuki developed it in a very great generality, but it was really first example of irregular Hodge theory, and it was really reproven by Saba and then by obviously Vologodsky using Vedic methods. Yeah, so it's still not terribly well understood result. And also what we understood, it's not for, actually it's related to the SIG as well. Yeah, we found a very general formalism. It's starting from DV algebras, something called algebra with bracket and differentials, it's the same property, and with satisfying this degeneration of Hodge to the RAM, the subset property. Then we can produce something called Frobenius manifold, n plus 3. So that's the choice. Produce Frobenius manifold which essentially can encode quantum products depending on parameter. So it was so we do not go through categories, we go through some more commutative language, which produces Frobenius manifolds in the same way one can do like this. Yeah, so it was a way to formulate mirror symmetry without categories. And I feel kind of very unhappy about it. So what we see is that it's homology of polyvector fields is a formal DGL algebra. And then I started to ask, but how it's related to non-commutative deformations? And it leads to me naturally to deformation quantization. Maybe 697. So what essentially I proved this cohomological quotient complex when A is algebra of some functions, smooth functions, or functions from smooth algebraic variety. Is quasi-isomorphic as the algebra of sections of stack algebra of polyvector fields. Yeah, and then if you go to global situation, it's so this deformation quantization was really important things to patch the whole things together. Instead this is general BV algebra formalism, we need also quantization to fuse this together. And there is something really interesting here goes on. So it's you see the homological deformation quantization should be part of formulation homological mirror symmetry. It's this isomorphism which goes here, and here it's canonical. But there are many canonical isomorphisms. What I discovered, it was kind of real story. There are infinitely many. There's a section of what's called Grothendieck Müller group. This multiple zeta values acts on it. So it means that multiple zeta L's somehow acts on identification of object in mirror symmetry. And it's still no, people do not really study it. Yeah, so it's something yet to study. Yes, so it was and then Dmitry Tamarkin found really great another book for deformation quantization result of mine using the link conjecture, which was unfortunately was not proven. Yes, he found a mistake. Yes, it was kind of very convoluted story with some mistakes. And then about maybe 99, 2000 with Jan 71. We work out some still in one of possible proofs within conjecture. But our proof was using this ribbon graph and not some combinatorics. It was really geometric proof. And then I started to return to this old idea that this ribbon graphs and infinite algebra should be related to so on. Because it's how one thinks is really, yeah, but you see that mirror symmetry was not really homological mirror symmetry was in kind of bad shape at that time. Maybe I can tell you what was going on in parallel front of homological mirror symmetry of categories. Yeah, so with Kenji Fukai also realized there's a big trouble, and then there was kind of limbo state for a while. And then in '97, Kenji visited IHÉS. And I proposed him idea about what's called how to get this trouble when you get a disk with boundary on your variety. First, it was very geometric. For example, I said, imagine we have some three-dimensional Lagrangian sphere, and there is a disk, and there is a disk with boundary on this sphere. But because the sphere is contractible, we should glue this disk by some disk inside the sphere. But then will be another disk, then into sectors, and then I can kind of correct things step by step. It was kind of very cumbersome procedure, but eventually we can do something. Yeah, eventually it was simplified algebraically, completely formal way. Yeah.
Sorry, before we change topics, there's a question. Vivek Shende asked, can you give us a repeat of how, what the relation was between deformation quantization and mirror symmetry?
Yes, about deformation, you see that there was this cohomology of d-bar forms precision with polyvector fields produce here Frobenius manifold. It was pretty formal Vitaly-Milkovsky algebra which we found with Sergei Baranikov. And this should be mirror symmetry to this guy. But then, according to this categorical conjecture, I should work not on polyvector fields, but on cohomological Hodge complex, which is something which has only cohomologous polyvector fields, but a priori could be different. And then it leads to me this equation. These things should be also canonically identified, polyvector fields and cohomological Hodge complex. That was actually the reason for cohomological mirror symmetry. I never stated in my paper on deformation quantization that this real reason was mirror symmetry, but there are other reasons, of course. Okay, yeah, so now I go to this thing. Yes, and then I started to, and with Jan, I started to discuss it and how to do this again, ribbon graphs and so on. And eventually to relate two worlds. This, sorry, I interrupt myself. Yeah, in 97, Kenji visited IHÉS. And then I proposed this idea of boundary cut chains, and it's kind of unlocked the whole subject. And he said, "Okay, let's write these things together." But then he went back to Japan, and I was here, and it was kind of a limbo situation. And then about 99, I think it was a bit funny. So I found in my emails what went on. Yao proposed to both of us, "Why don't you write a book about it?" And this is the next exposition, and I wrote, "Okay, let's do it." But then he said, "Okay." But then I said, "Oh, sorry, I'm very busy with Jan Sobilan. We're thinking to write something about deformation theory. I cannot do two things together. Maybe you can just continue the things." Yeah, so that's how it didn't became another time co-author of another important paper. Very symmetry. So, and then he collaborated with Okta and Honor. And for about maybe 10 years, this final version was maybe 2007. It took a really long time. And then there were a lot of controversies. Some people didn't believe. Fortunately, I wasn't there, so I was very happy not to participate in these controversies. So those different things, kind of with Jan, we started to think about graphs, operators, and in 2003, there was in Edinburgh was a centennial conference of William Hodge, and I gave a talk on this lecture. At the time, kind of figured out roughly how to what are necessary parameters from this abstract algebra category to get this ground between invariants and all this classing of the spaces. The trouble is the following. The story is the following. If we have infinity cyclic infinity algebra, then you get something called Hodge homology. It's not Hodge homology, it's Calabi-Yau, it's more the same. And then it maps to chains. This was the generation of my old construction of modulus space of genus G curve with n points, but each point has a tangent direction. So it extracts one bundle on the space. So this map to slightly wrong space, not bar, and this is directions. And then I said, this is what is necessary to go, but we want in ground between invariants to go to chains of another space and gen bar, a stable curve which degenerates. And one should kind of mod out by this rotation. And what I propose is that in this talk, that the necessary data, it was degeneration of Hodge-Durand spectral sequence in some abstract term. Namely, consider cyclic homology, negative cyclic homology of algebra. It's a model over from power 6 non-variable u, which is actually considered homology of CP infinity. of both element. So strength space over rotation group. It's a module, and degeneration means that it's a free module. It's a vector bundle, and you choose a trivialization of vector bundle. Identify all fibers with zero. Yeah, that's what's necessary extra things. Also satisfies some duality property. And then it's and then from this you can reconstruct homological class of N-bar and get this wrong semantics from categories as well. Yeah, so it was a proposal which kind of eventually generates moved to two different papers, because and not everything was documented at this 6. Yeah, so this 6 is with Jan Söderman, we constructed the section of chains and also wrote some foundation for infinity categories and blah blah blah. And then also there was another thing with Lyudmila Katsarkov and Tony Pantev. We also wanted to write about this trivialization of Hodge to Duran, and then we got just concentrate really more concentrated on Hodge surdic aspects and wrote devoted entirely to Hodge theory for such categories and so on. And there's a lot of speculations, conjectures. There's also one of the things which we discovered by accidentally simultaneously with Iritani, something called gamma class conjecture. If one look at all this mirror prediction, what is integral lattice of cohomology, how it sits like, already in the first calculation of Deleuze green parks, those zeta of 3 appears, and those values of zeta of odd integers appeared, but not multiple zetas. And this is related to this thing which is completely mysterious up to now. There's really no explanation what is going on. Yeah, yeah, but there was, and here there was kind of, yeah, so it was kind of two different directions. Vizian wrote some paper, kind of write definitions of good objects and triangulated categories. And for example, this notion of saturated categories by Bondel and Kaplanov, I separated in two issues related to smoothness and compactness. And then people in the article committee took it up, like Chantoin, and also later Lurie, Jacob Lurie realized that it's general class of dualizability, high dualizability, and all this stuff was kind of two-dimensional example of cobordism hypothesis and so on. Yeah, yeah. And then I thought it was a plan how to marry these things together, and some aspects we didn't write, and some people discovered, like Sergei Shadrin in the section of given type book, how the section of trivializations change the homological field theory. This is universal formula, which didn't bother to write at the time, but then eventually came up anyhow. Yeah, so it was this project. It started in 2003. Now I'll just briefly go to this later development. There was really very, very major development in 1996. SYZ conjecture. Stromer-Yau-Zaslow conjecture, which they say that if you have mirror manifold, they project to the same base. Let's with the complex dimension n. It's also the complex dimension n, but the base will have real dimension the same n. And the fiber will be tori, and it will be dual tori. And then they said that, and then it was something a little bit unclear. They said that tori should be special Lagrangian. And it was kind of first geometric picture. What is really goes on geometrically, not abstract equivalence of categories, but geometric picture. Afterwards, we realized it's kind of talked very, very well with categorical picture, because if you have Lagrangian torus, it's an object. You put U1 local cis, it's also should be an object, should be pointed on as manifold. Yes, that was a rough picture. But it was really a bit not clear what was going on around singular fiber. Should one believe literally this to get special Lagrangians or not? And Dominic Joyce produced some evidence that it should be not, should be something more complicated. And again, with Andrei Todorov, we discussed this picture and then realized that it was kind of, this picture should be really understood that the tori are very, very thin, very small. And there's some locus when there's singularities. We do not say anything about singularities, but outside singularities, it will be really dual tori. So it will be approximate statement. And then it leads to us with Jan to with Jan Söderman, we developed some non-Archimedean fiction. So everything depends on a small parameter. And we introduce the idea that it should be related to the Berkovich spectrum, things treat on kind of series and non-variable. It's now adopted by everybody, I think, in this mirror symmetry community story. Yeah, and it was a different relation. I will be very, very brief. It's not related to categories. Yeah, so with Yuri Chinkin, we have non-Archimedean Calabi conjecture, replacement of Calabi-Yau metrics, and it was solved and so on. And then with Jan, we start to think about the following. Suppose we get the space, it's kind of very, very small tori, progression very, very small tori, and how to reconstruct the dual space. It will be model space of object in Foucault category. But this is famous problem of this bad Lagrange manifolds when disk has which are boundaries of the disk. And then this main observation she made that if you look kind of suppose a base like a sphere or something, and singularities on the base have codimension 2, and then we try to see what does it mean that you have holomorphic disk. It produced some kind of tree with rational slopes which enters at singularity and boundary. And if you look count the dimension, you see that generic point doesn't has no chance to lie on this tree. It's a really like countable dimension of trees, like the two-dimensional surface. So the irrational point doesn't lie on these trees. So it means that I get actual object for Foucault category, and I get good coordinates here. So you don't have this trouble with M0. And if you cross the border, you have some change of coordinates. And that leads to wall crossing. It's completely different developments. It's quite was for many years and appears in other disguise later. And then it eventually leads to something called Gross-Siebert program. So how one really can construct mirror manifold, burn infinitely many walls and glue things together. And there are recent alternatives by Tony Yu and Sean Kill. Yeah, but it's reasoning it really goes through kind of like category theory. Things you have actual model space of object to get some good coordinates, and then it leads to the whole story. Yeah, so it was. So eventually, it's clear that in mirror symmetry there are two kind of mirror things. It's homological mirror symmetry and SYZ, and they should talk together. Yeah, and then there was still another development. Physicists became interested eventually in the things. Yeah, it was our mathematical game. We were very happy with this. But then physicists started to pay attention to these things because these things are called D-branes. Maybe it was introduced a bit later. And then Waffer realized that there's also mirror symmetry for D-branes, which is my homological mirror symmetry at the end of the day. But then Mike Douglas realized that there's something very tricky goes on from point of view of physics in this home space between coherent shifts, Lagrange manifolds. This is a grading by integer numbers. And this grading was not obvious at all from point of view of physics. He started to think about this grading. And then he proposed, then he started to see about actual D-branes in physics and what is going on, and make some kind of heuristic. So throughout 2009, heuristics about kind of harmonic objects and how they appear and disappear if you change parameters. It was so he said that you change parameters, then sometimes object decomposed by 2 and so on. And then Tom Bridgeland invented. He talked to Douglas, and he found kind of very beautiful abstract algebraic formulation of what is going on. It was notion of stability in translated categories. And the main thing that K0 of your category should map to complex numbers. In fact, it's R2, and R2 is oriented. Yeah, it's something which mathematicians never thought before, but it became natural for physics of central charge. Yeah, this became a very, very active area of research. And I was after that time I really got really interested about this relation to region stability of all this picture. That was the most mysterious thing. Yeah, what started to happen at this time? At that time, I think it's actually mirror symmetries, categorical mirror symmetries start to really appear as science, kind of science, because we have some kind of really maybe around this turn of century, kind of new people appear, because before we were more or less alone with Henry Foucault in this thing. So Paul Seidel, Vinyarou, Lyudmila Patsarkov, and then Mohammed Abu Zaid. So we have kind of really more people now. We have many people. Yeah, so it's a big community. And for example, Abu Zaid in what they proposed, it was a really great idea of wrapped category, which is the following. It's in a very simple case. You can see, go to non-compact varieties like cylinder, and consider infinite line R in R plus S1. It's Lagrangian manifold. And you want to define what is a home space of this guy to itself, and you start to kind of twist your cylinder more and more, and you see what's going on. If you consider copies that intersect infinitely many times, L twisted. Intersect this N will be vector space with basis integers. And then we can try to identify it with Laurent polynomials in one variable. So you get algebraic endomorphisms will be Laurent polynomials in one variable. The basis will be intersecting points, which will be by integers. Yeah, that's greatly open perspective. One can have new spaces to think about it, and then around 2009, I gave another talk on Arbeitsstagung. When I proposed the idea that not to change really Foucault categories, some should consider not Lagrangian manifolds, but maybe singular Lagrangian manifolds. But in order to define what is the right object, you put kind of local system with some kind of blue data, get some kind of sheaf, so canonical sheaf of categories. It was heuristic picture, and it was related to micro-local support, and now it's called stops in Liouville domain by Garnatra, Pardon, Schende, and there's a lot of activity here. And I think also with Jan, 2-3 years ago, we proposed what we said kind of better definition of Foucault category based on these guys. Yeah, it's still under development. Now, the trouble with this subject is that we work about something which didn't really have a definition, or even if some people have definitions, there's no common definition. Say, oh, okay, I prefer to do things in my way. So eventually, we cannot go to technical details because there's really no common ground. Yeah, so So it's a little bit of a mess, and one need kind of new hierarchy to clean this mess and produce kind of definition which would be convince everybody.
Maxim?
Yeah.
As a classical role of the chair is to tell you that it's 10:25.
Yes, yes, okay.
Meaning you have about 5 minutes.
Yes, yes. It's. I just want to almost finish. Yeah. Yeah. Then there was about still kind of unfinished project about 2014-15. I started to think about different things, which I think should be the future of the subject. If okay, category is coefficients. So what was the rough picture? And as the picture, we have collapse of Calabi-Yau varieties when fibers are real tori and collapse to zero. But when we can consider different types of collapse, the fibers are Keller subvariety of certain dimension. Like the product of two guys and fibers will be very small. When you consider collapse in small fibers, and if you're interested, so you get something which is kind of small, but not tori, it will be something more complicated. The base. Then, if you're interested, what will be special Lagrangians submanifold here? The special Lagrangian will be special Lagrangian of fiber on singular special Lagrangian on the base. Yeah, so you get really this picture, and what happens? You get a local system and local system of object and some local system of categories. And this local system of categories can have single fibers when the system degenerates. It leads to some notion of perverse shift of categories, which is now very active development by Kapranov and Schechtman. Yes, that's called Schroeder's. And also the whole thing is related to stability. The stable objects should we go to this thinking. Yeah, so those we had kind of for many years a discussion with Ludmil Katsarkov and his from a pundit in this room. Endless discussions, and it's still a very, very complicated story, but I think it will have a bright future. Yeah, so then there was also another topic one can include describing in floor theoretic way categories associated to Artin stacks. For example, we divide by affine line by GM, which is not further apportioned. And turns out that there are categories of coherent sheets on this guy. Is focalized category for the potential which is not polynomial but exponential. And if you draw the picture in terms of this skeletons, you get infinite this kind of infinite picture, which relates to gamma integrals, gamma functions. Yeah, so it was another interesting story. Yeah, so the whole thing is now in a very good shape. This original, although this definition are not very happy, kind of people found a way to get out. It's called generation criteria by Mohammed Abu Zaid. It's in a good situation. You can describe your category, although you don't really happy with construction. And then you can prove mirror symmetry. It's more or less following this deformation theory ideas by Nick Sheridan. It was already 10 years ago. He put eventually homological mirror symmetry, certain formulation for Calabi-Yau hypersurfaces. Yeah, so soon it will be kind of all package with operators and so on will be finished. I'm pretty sure there are a lot of people. Yeah, so there are other subjects. For example, there was something called coisotropic brains introduced by Kapustin and Orlov in about 2001, which I originally didn't appreciate, and was almost really no work on it, but I think it's really has a really great future. This coisotropic brains, which is for which we have really no idea how to approach them, but there are many things. And then also with Jan for maybe 5 or 6 years, we work on generalized Riemann-Hilbert correspondence. It's kind of another mirror symmetry type statement for which we don't even have heuristic, but it's great mathematics related to wall crossing and resurgence and so on. Okay, thank you.
All right. Well,
okay.
Thank you very much, Maxim. So, so far the audience has asked just about as many questions as the undergraduates in my Zoom classes. So I think we have time for a couple of questions. You type in the question and answer box, and I will read them out. While you're typing it, I have a question of my own. So when you just said this, Artin stack, you said the potential e to the x gives rise to some kind of function. What functions?
Yes. No, eventually you kind of integrate exponent of the IHÉS bar of some vanishing cycles. And cycles more or less like this. In general, if you get potential, you look in some exponential integrals depending on small parameter, But here potential will be exponent. You try to make convergent integrals of it, and then you get values of gamma function.
Of gamma function.
Yeah.
May I ask a quick question while people are typing their question? So I know that I asked you this question literally every year, and I ask every year because I want to know what's the development. So on the Fukaya side, what is the current prediction on calculation of enumerative invariance, counting Lagrangians of manifolds and things like that?
Now, counting Lagrangians, one can expect only in 3 dimensions. Now, there is theory of Donaldson-Thomas invariance, which is in touch here,
but on the Fukaya side, there has no.
Yeah, no. In principle, in S-phase picture, one can see what is going on with this counting. I don't know. This is progress.
Any question? Oh, there is a question, Paul.
Yeah. Yes, there's a question from. Actually, several questions. Okay. So one question was, if it is possible, you could say a few words about how tropical geometry goes into this.
Yeah, it's by various reasons. For example, in this S-phase picture, we consider how holomorphic curves look like in the limit. You get straight lines with rational slopes. Yes, that's basically.
Okay. And the other question is, yes, it's actually, so why is this e to the z the correct mirror for this Artin stack? And, how is this an example of a more general?
Oh, yes. The story is the following. I think it's what mirror to A1 is C star is coordinates equal x. And the potential is equal to x. It's non-proper map. Yeah. Now we want to divide by gem, but kind of dual group to gem is z. And mirror symmetry means that you go to universal cover of C. And then x will be right as exponent of z.
Okay, there's one more question. An anonymous question. It is a long-standing conjecture that the Hodge numbers can be derived from the derived category.
Actually, I don't believe it. I don't believe it. So here again, consider near kind of double limit and mirror symmetry. There is additional monodromy which allows to reconstruct Hodge numbers. It's no. In non-commutative geometry, what we can see only Hodge numbers HPQ see only P minus Q as a parameter.
All right, if there are no more questions, then thank you again, Maxim.
Thank you.
Very much.
Well, thanks a lot, Yasin. That's very nice.
Thank you. Thank you.
Great talk.
Okay, thank you. I hope to write it. Yeah.
Thanks.
Yeah. I certainly hope so. It will be very important, useful.
Okay.
Thank you.
Okay, thank you.
Yeah.
Okay.